Okay, welcome back everybody. So we have been looking at the extreme value theorem, figuring out whether or not we are guaranteed a min or max on an interval for a function, and also then taking that, finding those candidates and seeing if there are mins and maxes. And right now, the only way we have to tell whether something is a min or a max is to start testing the y values. And let's be honest, that's kind of a gross way to do it. It doesn't seem very calculus-y. It's not very sophisticated at all. So here comes the fancy way to do it, and it's called the first derivative test. Okay. What the first derivative test does is it basically gives us a super quick foolproof method for figuring out if something is a minimum, a maximum, or neither, right? Just because it was a candidate to be a critical point doesn't mean it is. Right? Not all candidates are winners, as we know. Okay, so what it's going to have us do is look at the first derivative. First derivative is going to tell us what the function is doing as far as its slope, right? Positive slope means function is increasing, positive slopes, negative slopes, we have a decrease. So we're going to look at that, the sign on the derivative, also known as the slope, and decide, well, was that at that point, was it hitting a min or was it hitting a max? Okay, so here's the text of it. Looks like this. I'm having some technology struggles today. I'm not going to lie to you. Okay, here's the text of it. It says, if f prime changes sign from positive to negative, then there's a local max at C. Think about what this means. Let's think about a sign chart here. Got this cool sign chart. I'm calling this point C. I say, hey, my derivative was positive. At C, it was 0, and then on the other side of C, my derivative was negative. Okay, well, that means that it was increasing, positive slopes. And then at C, changed its mind and started, decreasing. That, my friends, is a maximum. Okay? And we know that that can occur two different ways. Maybe it was because the derivative was equal to 0. In which case my graph would look something like this, right? It was a smooth transition. So my function was increasing and then it was decreasing. Right? So the slope slowly approached 0 and then it slowly went away from 0. That's going to be a max. It can also happen at a point where the derivative fails to exist. You're going to have a nice little pointy place, but it's still a maximum. That's why you have to remember to look both places. We'll talk about endpoints in a minute. Okay. If the opposite is happening, that means you have a minimum, right? So if you have a derivative and it changes sign from negative to positive, look what your sign chart's going to look like. I have a function that is decreasing, and then all of a sudden at C, it goes to 0 and then it starts increasing again. That's a minimum. It decreases and then increases. Minimum. And whether it does that smoothly and gives us a 0 derivative, or abruptly and gives us a derivative that fails to exist, it's still a minimum. Now, I don't know whether it's an absolute or a relative min, but I know it's a minimum. To figure out if it's absolute or relative, we're going to have to look at things like end behavior and the other y values. Okay, so it's also important to note, just because a derivative is 0 or undefined doesn't mean it's necessarily a min or a max, right? You can have a critical point. You can have a candidate that isn't a winner, right? And that is this case here. So I have a function and it was increasing. Slope went to 0 for a sec and then it kept on increasing. That's not a min. That's not a max. That's a nothing. It actually is an interesting point, but we'll talk about it later. Okay. Over here, look, it's decreasing, hits 0 or goes undefined for a second, and then decreasing on the other side. This is a piecewise function, right? Where I have a function that's decreasing and another function that's decreasing, and I've pieced them together at this point. Where they come together, the derivative fails to exist. It's not a min, it's not a max. It's just where they happen to come together. Right? So sign charts are going to be super helpful in solving these problems. Okay, so where the derivative is equal to 0 and where the derivative is undefined, those values are going to go on a sign chart. We're going to test the intervals so we can see, is it changing from increasing to decreasing? Maximum. Is it changing from decreasing to increasing, minimum, or is it not changing? So it just increases and then keeps on increasing, or decreases and then keeps on decreasing. We also have to remember to check that third spot, the endpoints. So if a function, if we're on an interval, a closed interval, then we're going to want to put those endpoints on our sign chart as well. Okay, so let's think about something where we're on an interval. Oh, we're calling it A, right? So let's think about, let's say I have, the interval I'm on is A up to infinity. So I have some function like maybe like a square root function, right? It has a definite starting point and then it goes off to infinity. If that's the case, when you make your sign chart, you're going to have A, you're going to have a critical point right here at the end. Now, if it's at an endpoint, the thing is I can't look for a change in increasing or decreasing, but because there's no other side, like I can't look on the other side of A and be like, well, what was it doing over there? Fact is, it doesn't matter what it was doing over there. This is the beginning. So if at A, it increases after A. So in other words, I was here at A, and then my function started growing and growing and growing. Well, if that's the case, then A is a minimum. Look, it was a low point. It was at A, it was at some level, and then it's, oh my goodness, and then it's, and then it started increasing. So that would be a minimum. It can also happen, though, that as I leave A, I'm decreasing, right? So if this is my endpoint, and it's decreasing as it leaves A, then that would make this a maximum. Again, I don't know if it's relative or absolute, but I'll figure that out later. It's all about that, what it's doing as it leaves A. Right? If it's increasing, A is a min. If it's decreasing, A is a max. Okay. Other end, if you have a right endpoint, it's going to be the exact opposite of that. So at a right endpoint, so let's say we're on an interval from negative infinity up to some point B that is included. Now my sign chart is going to look something like this. So think about this. If this is increasing as it approaches this endpoint B, and then it gets to B, that makes B a maximum. In the exact opposite way, if I have a negatives on my sign chart, that means it was decreasing as it approached B, then B is going to be a min. Right? Now this is all very technical. If the derivative is less than 0 for all x less than b, that just means it was decreasing. Right? The derivative was negative for all the values before b. Like as you approached b, the derivative was negative. In other words, this thing was decreasing as it approached b. Well, then when it gets to b, that's going to be a low point. If the thing was increasing as it approached b, then b is going to be a high point. All right, so let's take a look at one. All right, so by the time we are done with this section, man, we're going to be able to look at any function, even if it's not a pretty polynomial, and make a sketch of it, basically. We don't need a graphing calculator. Nobody needs that anymore. Okay, so 2 questions here it's going to ask us. We want local and absolute extreme values. So we want to know where are the mins and maxes, but not good enough. We also want to know, are they local or are they absolute? Worth noting, I'll say it 100 times, some books call this a relative min or max. AP kind of goes back and forth with what they call it. Some books call it a relative min or max. Some books call it a local min and max. I fear that I also go back and forth. It means the same thing. Okay, and I also want to know intervals where the derivative is, or where the function, sorry, is increasing or decreasing. I can find all of this information from the first derivative. So let's take our first derivative. So I have 3x squared minus 12. So if I want my critical points, I need to know 3 things. Where does this equal 0? Where does this fail to exist? And are there any endpoints? Okay, well, let's think. Endpoints. It's a polynomial. This domain is negative infinity to positive infinity, right? It's a cubic. It starts at negative infinity. It grows to positive infinity. And since I'm in reverse on video, I'm going to do this for you. Okay. So it's starting at negative infinity. It's ending at positive infinity. So my sign chart is arrows on both ends. And that means something to me as well as far as mins and maxes go. If it starts at negative infinity and goes to positive infinity, there are no absolute mins or maxes. Can't be. It can't be. There's no high point, there's no low point. It goes down forever, it goes up forever, which means any mins or maxes I find are going to be local. All right. Now, does not exist. Again, it's a polynomial. Nothing exciting going on here. 0, though, that's a different story. This thing is going to equal 0 twice, at 2 and at negative 2. So all I have to do is set this equal to 0, solve for x. I'm going to find that it hits 0 twice. Once at negative 2 and once at positive 2. So I have 2 critical points that I need to take a look at. Again, you may not assume that those are mins and maxes. You might see one of those where it doesn't change. Got to check the sign chart. All right, so let's go. We'll test the middle first. That's the easiest part to test, right? Between negative 2 and 2 is our friend 0. And at x equals 0, this thing is equal to negative 12. So it's negative. So between negative 2 and 2, we have a function that is decreasing. Okay. After 2, let's test a value like, oh, I don't know, 3. Okay. So at x equals 3, I've got, what, 27 minus 12. That's positive. So I know that after 3, I have a function that increases. So right away, look, I had a function that was decreasing and it turned into increasing. I know what's going on here. On the other end, this is symmetrical. So I don't really even have to do a calculation. But if I plug a negative 3 in here, I still get 27 minus 12. So this is positive over here as well. So I'm going to look at my sign chart to get all of the information I need. Here's my intervals where it's increasing. Here's my interval where it's decreasing. I can look here and say, okay, it was increasing and then it started decreasing. That makes this a max. Here it was decreasing and then it started increasing. That makes this a min. Now, I wrote all that beautiful stuff on that sign chart. Here's what AP does. They don't care. They literally train the graders to put their hand physically over your sign chart. They will not look at it. It is our job to take all the information that they asked for in those questions and translate it, write it down. Anything on the sign chart won't get graded. I don't know. It's kind of rude, but whatever. All right, so we said no absolute min or max, so now I have to go over here, even though I already wrote it, and say there is a local max at x equals 2, negative 2, and there is a local min at x equals positive 2. They also want intervals of increasing and decreasing. So we'll say increasing on, and we're going to use interval notation here. So I'm going to say negative infinity to negative 2 and 2 to infinity. Now, we'll talk about this a lot more. Notice I did not include 2 and negative 2 in the interval, nor did I include infinity and negative infinity. You should never, ever, ever include infinity or negative infinity in any interval. They are ideas, not numbers, so they can't be included. Whether or not you include the 2 and negative 2 is actually up to you, depending on how you feel like defining increasing and decreasing. Now, I say I define increasing and decreasing using, oh, I don't know, calculus. And in calculus, we define increasing and decreasing with positive and negative derivatives. At 2 and negative 2, the derivative is neither positive nor is it negative. So it is not going to be included in any interval if you are defining increasing and decreasing using calculus. Some textbooks, probably the same ones that say pointy place, define increasing and decreasing the pre-calc way by saying, well, it was increasing if each point is higher than the one that came before it. And if that's the case, then technically you could include them in both intervals. That's madness. Technically, AP will accept either one. I'm warning you now. They're not as easygoing on other topics coming very soon. If I were you, I would get in the habit of not including them, because you don't want to get caught including them in another topic and missing it, but also it's just the right thing to do. Just have some calculus morals and don't include them. All right, so anyway, that's my lecture for the day. Decreasing, we've got -2 to 2, not inclusive. All right, so from this, I could make a really pretty good sketch of my function, right? I know it starts at -infinity because it's cubic. It's going to increase for a while. It's going to hit negative. It's going to hit x at x is -2. It's going to start decreasing. At x is +2. It's going to start increasing again. I don't know the y values. I don't know how steep the little peaks and valleys are, but I know the general shape of the graph from this. And here's the picture. Not too shabby. Now, this is a polynomial. I'm sure there's more, obviously there's more complicated ones we're going to do, but we're still going to be able to get a pretty good idea of the shape of a graph from using the first derivative test. And there's another test coming called the second derivative test. It's going to tell us even more about it. Okay, so we will practice a bunch of these in class. For now, put any questions you may have at the end of the video, and we will talk soon.